In this video, we will discuss pressure in static fluids. The fluids that we consider are any substance that can flow and change the shape of the volume that it occupies. So for example, a fluid can be a liquid or a gas. And for fluids, we often use the density, which is represented by the letter ρ, and it is equal to m over v, where m is the mass of the material and v is its volume. Now, you already know all of this, but remember that in physics, the units of mass is the kilogram, and so for the density, it is kilogram per cubic meters. Now, in these tables, you can see a few values of densities. For example, air at 20 degrees and 1 atmosphere is 1.2 kilogram per cubic meters. And so picture a cube of 1 meter on the side, and this is 1.2 kilogram of air. Now, the density of water is 1,000 kilogram per cubic meters, so that's 1 ton, and so that's much heavier. And of course, there are many materials that are that have even larger densities. So, for example, mercury is 13.6 tons per cubic meters. Now, most of the time, we will work with materials that are homogeneous. But you should know that most materials are in fact not homogeneous. For example, the human body contains fat, which is less dense than water, and bones that are more dense than water. And so some people float, but some people who don't have a lot of fat don't float, for example. Now, what is less obvious is that even gases are not homogeneous if you consider a very large volume. Right? For example, if you consider the entire atmosphere, then the density decreases with altitude. And it is similar for large volume of water. For example, the ocean has several layers with various density. The Pickno line refers to the rapid change of density with depth, and it depends on things like the salinity gradients or the temperature gradients. Now, let's introduce the concept of pressure. So if you have a fluid, and if you consider a surface inside this fluid, then this surface has a certain area A, and the fluid will exert some forces of pressure on that surface that are perpendicular to the surface and that exist on both sides of the surface. Now, the fluid is at rest, so the forces are the same on both sides. And the pressure is, by definition, the perpendicular force divided by the area. And so it has units of pascals. 1 Pascal is the same as 1 Newton per square meters. And it is a small quantity, so we often use other units. For example, 1 atmosphere is 101,325 pascals. This is, in fact, an exact number. And the bar is another unit of pressure. 1 bar is 10 to the power 5 pascals. So it's almost equal to 1 atmosphere as well. Now, one important distinction between pressure and the forces is that pressure is a scalar. So it does not have a specific direction. Pressure depends on the altitude. And that is why when you take a plane, for example, the cabin needs to be pressurized. And it also depends on the depth. When you dive into deep water, you can feel actually the pressure in your ears. So we will show that the variation of pressure with altitude or depth is given by dP over dy is equal to minus rho g. So in this relation, P is the pressure, y is the height, rho is the density of the fluid, and g is the acceleration due to gravity. So to do this, we consider again a fluid. This time we consider a small volume in this fluid. The top and bottom surfaces have the same area A, and the bottom surface is at the vertical position y, and the top surface is at the vertical position y plus dy. Now, the pressure at the bottom is P, and so the force on the bottom surface is equal to P times A. The pressure at the top is P plus dP. We don't know dP, but this is what we're trying to calculate. and the force on the top surface is going to be minus P plus dP times A. The minus sign here is because this force is going to be downward and the y-axis is upward. The weight of the small volume is equal to minus mg, and the mass is rho times dV. And since dV is A times dy, then we can write minus rho A dy g. And now we can write Newton's law. Since the fluid is at rest, the sum of all the forces must be equal to 0. And so here we have three forces: the pressure at the top, the pressure at the bottom, which is upward, the pressure at the top, which is downward, and the weight, which is also downward. And so we have PA minus P plus dP times A minus rho A dyg is equal to 0. And you can simplify by the area A, and you can simplify P minus P, and then you obtain that dP over dy is equal to minus rho g. So this is negative, so the pressure decreases when you go up and increases when you go down. Now we can calculate the pressure as a function of position using this relation. So let's do it with an example. Let's say that we have a storage tank that is filled with water up to a certain level, H max. And let's consider the pressure at some position below the surface. And let's call this depth H. So we're going to calculate the pressure as a function of H. So let's integrate the relation on both sides. So we have integral of dP over dy is equal to integral of minus rho g. Now we do the integral from position 1 to position 2, so that it will give us the pressure variation between these two positions. So on one side we have the integral of dP, and on the other side, since rho and g are uniform, we can take them out of the integral, and so we have the integral of dy. Now this integral is simple. We obtain P2 minus P1 is equal to minus rho g y2 minus y1. And we can rewrite this as P1 is equal to P2 plus rho gh. And so if the tank is open to the atmospheric pressure on top, then P2 will be equal to the atmospheric pressure P0. And so the pressure as a function of depth will be equal to P0 plus rho gh. And so in this relation, P is the pressure at a certain depth H, and P0 is the pressure at the surface, and in this case it is 1 atmosphere, and rho is the uniform density of the fluid, and g is the uniform acceleration due to gravity. And h is the depth below the surface. So let's do an example of question. The classroom is 13 meters wide, 13 meters long, and 3.5 meters high. And the temperature is 20 degrees Celsius, and the pressure is about 1 atmosphere. So what is the change of pressure between the bottom and the top of the classroom? So the density of air in these conditions is 1.2 kilogram per cubic meters. And the room height is given as 3.5 meters, and we have g, the acceleration, as 9.81 meters per square seconds. And so you can calculate rho gh, and it is about 35 pascals. And so that is a number that is much smaller than the atmospheric pressure, which is 10 to the 5 Pascal. And so the variation of pressure in the room is really negligible compared to the absolute value of the atmospheric pressure. Now, one important result we obtain is that the pressure only depends on the depth h. It does not depend on the shape of the container. So one illustration of this is called Pascal's vases. Here I have a collection of tubes with different shapes and different volumes, and they are all connected to the same pipe at the bottom. And so when I add liquid into one of the pipe, then the liquid can travel to any tube. And all the tubes are open to atmosphere, so the pressure at the top is the same for all the tubes. And because the pressure only depends on the height, then the pressure at the bottom of each tube will only depend on the height. But once I let the liquid at rest, then the pressure at the bottom has to be the same for each tube, because otherwise the fluid will move. And so since the pressure at the bottom is the same, then it means that the height has to be the same in each pipe. And so even if there is a different weight of water in all the vases, then they still produce the same pressure. And this pressure is transmitted through the pipe in any directions because pressure is a scalar. Now, note that here it is important that the density of the fluid is the same everywhere in the demo with the Pascal's vases. Right? If you have a mixture of two liquids that don't mix, then you have two different densities. And so in that case, different height in each tube can be possible. For example, in this U-shaped tube, you put oil which does not mix with water, and you put oil in the right arm of the tube until the oil-water interface is at the midpoint of the tube. And so both arms of the tubes are open to air, so the pressure on top is P0 on both sides. But because of the different density of oil compared with the density of water, then the height in both arms is not the same. And the density of oil is in fact smaller than the density of water, and so the height of oil is larger than the height of water. Now, I said that the pressure is transmitted through the pipe in any directions because pressure is a scalar. And this is in fact known as Pascal's law, which states that the pressure applied to an enclosed static fluid is transmitted undiminished to every portion of the fluid and the walls of the container vessel. And so this means that, for example, that the pressure on the left of this container is the same as the pressure on the right, provided that they are at the same level, at the same height. And this can seem counterintuitive because if you look at this figure, there is less water above the left side than there is above the right side. But the pressure is transmitted, and if it was not otherwise, then there will be a flow of the fluid would flow. An important consequence of this is that it can be used to multiply forces. So consider the shape here with a large surface on the left and a small surface on the right. Both are at the same height, and so the pressure P1 is equal to the pressure P2. And since the pressure is equal to the force divided by the area, then we have F1 over A1 is equal to F2 over A2. And we can write that F2 is equal to A2 over A1 times F1. So it means that if you apply a force F1, then the force on the other side will be multiplied by A2 over A1. And so this is like a force multiplying device. And so this is the principle that is used, for example, for car lift or for hydraulic brakes, right? A small force can be multiplied into a large force to have more braking power. And for example, also this is used for pallet jack and many other things. Now let's come back to the relation that P is equal to P0 plus rho GH. This means that you can read the pressure by reading the height h. Right? And this is what we call a manometer, which is a way to measure the pressure. In this relation, P is the absolute pressure, and if you don't know P0, then you can give the gauge pressure, which is P minus P0. Right? Now, before we discuss manometers, let me show you something you probably already noticed. Right? I have a big bowl of water. I've added a bit of grape juice so that the water is not completely transparent, so that we can see a little bit better. And now I'm going to fill a glass in it. Then I lift the inverted glass, and you can see that the level of water is rising into the glass. The forces of the atmospheric pressure are able to keep the column of water inside the glass. And of course, if I pull too much, then air is able to enter the glass and all the water falls back down. But let me ask you a question. How high can I lift water like this? Let's say that I have a huge bowl of water, or let's say that I am in the middle of the ocean. So I have all the water I want. And I have a gigantic, super tall glass. Is there a limit to how high I can pull the water up like this? And so let's look at this situation in details. At the top of the glass full of water, we have the pressure P. And at the level of the water in the big bowl, we have the pressure equal to atmospheric pressure. And this is because P only depends on H, and it is at the same level as the surface of water in the large tank. But at the same time, this pressure must be equal to P plus rho GH, since this point is below a column of water in the glass. And so I can rewrite the pressure on top as P atmosphere minus rho GH. And so you see that the pressure in the water that is in the glass is lower than the atmospheric pressure. That is why the pressure is the water is there, right? It is pushed on one side by the atmospheric pressure, which is larger than the pressure inside the glass. Now you see that if the height is very small, if the height is very large, then the pressure on top will become very small. But the pressure on top cannot become too small, right? It cannot become negative. So pressure is always a positive number. So that means that rho GH has to be smaller than P atmosphere. Now let's look at numbers. Rho for water is 10 to the power 3 kilogram per cubic meters. G is around 10 meters per square seconds, and the atmospheric pressure is around 10 to the power 5 pascals. And so H has to be smaller than about 10 meters. So you can have a column of water that is up to 10 meters high, like this, and after that, then the water on top would be 0, so you would have vacuum. And for liquid mercury, the density is much larger. So instead of 10 meters, then it is 760 millimeters. And so for liquid mercury, then if the column is larger than 760 millimeters, then you have a vacuum on top. And so the height of the mercury can then be used to measure the atmospheric pressure. The mercury barometer was invented by Evangelista Torricelli, and so the units of pressure are sometimes given in torr. 1 torr is the same as 1 millimeter of mercury, and 1 atmosphere is equal to 760 millimeters of mercury. Now, these mercury barometers used to be popular, but have been replaced because of the toxicity of mercury. Maybe your grandparents still have one. Right? It is a long tube that is at least 76 centimeters tall, and at the top there is vacuum. And by measuring the height of the column of mercury, then you can deduce the atmospheric pressure. Now, one issue with this type of barometer, in addition to the toxicity of mercury, is that the density of mercury depends on temperature, and it's not depending on temperature in a perfectly linear way, and so you need to account for the temperature. And also because the acceleration due to gravity, g, depends on altitude, then the pressure reading will also depend on altitude. So that kind of barometer is not very precise. But we still use the units of millimeter of mercury for the pressure. Right? When you take your blood pressure, you get 2 numbers, and those numbers are in millimeter of mercury or torr. And since the pressure depends on the vertical position, then there is a standard reference to measure the blood pressure, and it is at the upper arm so that it is level with the heart. Now, the principle of the atmospheric pressure being used to lift a column of water or a column of mercury can also be used to lift objects. For example, here I use this rubber mat on the top surface of a stool, and then I can use this to lift the stool. Right. What holds the stool against the rubber mat is the atmospheric pressure. There is no glue, there is nothing like this. Right. The atmospheric pressure at the bottom surface of the stool is pushing the stool up against the rubber mat.